Hey guys, this is Mrs. Rajewski. Today we are going to talk about the convergence of the Taylor series. So, since we already know that a Taylor series is a form of a power series, we also know that every Taylor series has to have an interval of convergence, just like what we did when we were working with the power series. When that interval, so we're gonna use this capital I for, when that interval of convergence exists on the set of real numbers, then that means that the power series can be used to find the value of that function for every single real value of x. But sometimes that interval of convergence is going to be bounded. And that means that it's not going to work for every single value of x, but only some specific ones or on a particular interval. So not all of them, but a restricted interval. Then we can only use it to find values of f of x that are actually in that interval. And I think that's pretty intuitive, right? If we know that there's an interval of convergence, it will only converge upon that interval for those specific values of x. So, for example, here I've got the function 1 divided by the quantity 1 minus x. And we have worked with this function or something similar previously, and it corresponds with the Taylor series, the sum from n to infinity of x to the n power. Now, if we test an n value, or an x value like 1/2, we're going to get a converging series. So this is going to converge to the value 2. But if we choose a value for x that is larger than 1, such as 5, then our function is just going to keep growing and growing and growing and growing. So just as long as our x values are in between -1 and +1, we'll have a converging series. But as soon as those x values are on the outside of this interval, aka the interval of convergence, then our Taylor series falls apart and we can no longer use it. So what we do have here is Taylor's theorem. So Taylor's theorem says that a Taylor series will converge if and only if the limit as n approaches infinity of the absolute value of the error is equal to 0. So there is no error, therefore it converges, right? Okay. Let us continue. So let's use this to show that the Maclaurin series for e to the x is valid for all x existing on the set of reals. Now, you might be like, well, is there a special Maclaurin theorem? No, silly. Remember that the Maclaurin series is just an extra special Taylor series that's centered around the value 0. So we can use the Taylor theorem here as well. So basically, I have a plan. My plan is to show that the error term has a limit as n approaches infinity equal to 0. So let's get to it. So I'm going to write down my plan so we know what it is. That's Taylor's theorem. Now, with e to the x, which is oh my goodness, that's a terrible 0. E to the x is a really fantastic function because its derivative is itself. And then the next derivative is still itself. So we know that the nth derivative with respect to x is equal to e to the x. We also know that the next one, the next derivative, I should say, of x is also e to the x. And this is true for all n existing on the set of integers. Remember, n has to be an integer because we're talking about its place in a series of numbers. Okay, so therefore, we know from our rules about the error term for the nth number in the series, so the nth term in the series, is equal to the absolute value of the next derivative, so the n plus 1 derivative with respect to c, times x to the n plus 1, all divided by, big absolute value, n plus 1 factorial. And if you're confused about this, you could go back in and look at our Taylor approximations and our Taylor series And then, of course, C is, there exists a number C between 0 and x that makes this error true. Okay, so let's plug in what we know. So I just stole this from our prior lesson and to calculate the error term. So I know our next derivative, well, every derivative is always going to be e to the x, but we're taking it with respect to c, so I'm going to substitute in a c for this x value here. So I'm going to get the absolute value of e to the c power instead of e to the x times x to the n plus 1 all divided by n plus 1 factorial. Whew. Okay, so now we're going to go ahead and we're going to simplify this and take the limit, because to show that the Maclaurin series is valid, I really do have to show that the limit as n approaches infinity of this absolute value of the error term is equal to 0. So I have to take the limit. So let's do that. The limit as n approaches infinity of the error term is equal to the limit as n approaches infinity of this thing that we just found right here, the absolute value e to the power of c times x to the power of n plus 1, all divided by the quantity n plus 1 factorial. Okay, so let's think about logically what this means, all right? I'm taking the absolute value of this whole thing. Well, e to the c power, this is going to give me a constant, and I know that e to any power is going to be a positive number. Similarly, n plus 1 factorial, n has to be a number that's 0 or higher, because we're talking about where it's at in the series of numbers. So I'm always going to get a positive number here. It's never going to give me a negative. So the only thing I have to worry about, what its sign, and the reason I'm talking about this is because we're taking an absolute value. The only thing I really have to worry about is this x value. So I can simplify this a bit. So I have the limit as n approaches infinity of e to the c, which is going to be positive, times the absolute value of x to the n plus 1 power. The only thing I really have to worry about the sign here is x, all divided by n plus 1 factorial. Okay, so what are we going to do here? I don't know what e to the c power actually is, besides the fact that it's positive. So I'm going to just explore some thoughts here. If you know me, you know what time it is. It's time for an aside for logic. This is where we take things that we know and try to make some connections to things that we're going to figure out. So I know that e to the c power has to be greater than 0. I also know that n plus 1 factorial is greater than 0. Additionally, we just talked about why the absolute value of x to the n plus 1 power is the same as the absolute value of x to the n plus 1 power. So we also know up here, when we were defining the error term, and if you go back and look at when we first were defining the error term, that c exists in between 0 and x, right? So we know that is true. So we know that x has to be bigger than 0. Okay. And we also know that 0 is less than c, and c is less than x, because we did just say that there exists some c value that's in between 0 and x. So I'm just basically putting it in an interval here for us. Okay. Then this must mean that, what if let's just remember, it's an aside for logic. What if I exponentiate? Then I've got e to the 0 power, right? Or even just 0. Let's go there. Is less than e to the c, which is less than e to the x. I could put in a 1 there, but I'm not really sure if 1 is going to help me out with this e to the c. But I do know that 0 is my lowest value here, so I can keep that there. So all I've done is I've just exponentiated. I love to exponentiate. You know, it is my favorite E word. So now I've exponentiated, and the reason I did this is because it kind of created, well, it definitely created that e to the c term that I was looking at. So I do know that whatever e to the c is going to be less than or equal to my maximum value. My maximum value is going to be e to the x power. So e to the c is going to be less than or equal to, I'll call it m, my max value. Okay, and our max value also has to be a real number, so let's just go ahead and define that. Say that it's on the set of rails. Okay, whoa. So you might be thinking, what are we going to do with this aside for logic? We just kind of talked about things that we know, we extrapolated a little bit. Well, I can say that at least, while I might not be able to calculate the limit as n approaches infinity of all this, because I don't know what c is, I can, however, say that all of this has to be now less than or equal to the limit as n approaches infinity of my max value times the absolute value of x to the n plus 1 divided by n plus 1 factorial. Now, how do I know that it's less than? Well, because I know that m, my max value, is greater than or equal to e to the c. So if I replace e to the c with m, the result is also going to have to be greater than or equal to this original. Now, I don't know what my max value is, but I do know that it's going to be a constant, just as this was a constant. And with limits, I can move this out to the front. So here we go, out to the front of my limit. And I've still got the absolute value of x to the n plus 1 power, all divided by n plus 1 factorial. Sorry, that got a little squishy here from one line to the next. Now, this makes me dance the happy dance inside because I see this here. This is a well-known limit. You can explore it graphically if you would like to, but this limit is equal to 0. It is a very useful limit to know. So now that we know that it's equal to 0, what have we got here? Well, my dears, what we have here is that this is going to reduce to m times 0, which is 0. Well. What that is, if I bring it on down, all the way down, what this is telling me is that the limit as n approaches infinity of my error term is less than or equal to 0. Well, it's an absolute value, friends. Clearly, the limit as n approaches infinity is going to be greater than or equal to 0. It's an absolute value. So what does that mean? If I'm telling you that it's less than or equal to 0, and I'm also telling you that it is greater than or equal to 0, What does that say? Well, hopefully you figured it out logically. That means that the limit as n approaches infinity of this error has to equal 0, because it can't be less than 0 and greater than 0 unless it actually is 0. Well, it has to have those equal signs in between. So, and this is true by the Squeeze theorem. Well, it would help if I could write Squeeze theorem, huh? So what did we do? Well, we just showed that the Maclaurin series for e to the x is valid on the whole set of real numbers. If you recall from prior work, that Maclaurin series for e to the x was, let's write this a little bit less sloppy, Ryeski. X to the k power divided by k factorial for all x existing on the set of reals. Fantastic. All right, so let's try another one. Again, we're going to show that the Maclaurin series for the cosine of x converges to the cosine of x for all x existing on the set of reals. Pretty similar to what we did on the last one. So here we go. From prior work, we know that all of the derivatives are either going to be positive sine of x, or whatever variable you're using, negative sine of x, positive cosine of x, or negative cosine of x. So I'm just going to write that down. I'll use t for my variable. And you might be wondering, okay, yeah, so what? But what that basically tells us is that the absolute value of the derivatives has to be less than or equal to 1, because sine and cosine both have maximum values of 1, and they also have minimum values of -1. If we're talking about absolute value, which we are since we're talking about the error terms, then their absolute value is always going to be less than or equal to 1 of their derivatives. And also, I guess, the original functions. And we're taking it with respect to c. What this means is that the absolute value of our error term, for however n many terms, is equal to the absolute value of the n plus 1th derivative of c times x to the n plus 1, all divided by, you guessed it, n plus 1 factorial. So this is how we calculated that error. Now, we know that if when we substitute in this c value that's somewhere in between 0 and 1, we're going to get a constant. And that constant, when we take the absolute value, is going to simply be the absolute value of the nth plus 1 derivative. And again, if we take the absolute value of this factor, that's going to be the absolute value of x to the n plus 1. And we do know that the denominator, n plus 1 factorial, is going to be positive regardless. I still kept my absolute values around this guy because we could have negative results, so we want to force it to be. I would like to show that the maximum value is 1. So let's go ahead and go there. So we're going to say that if I use the maximum value, this whole thing is going to be less than or equal to what our maximum value would give us, right? Hope I didn't lose you there. Okay, now, since the limit as n approaches infinity of the absolute value of x to the n plus 1 divided by n plus 1 factorial is equal to 0. Then this guy, when I take the limit of it, I'm going to get this whole piece equals 0 times 1, which is 0. So we're going to get that the limit as n approaches infinity of the absolute value of r sub n of x, remember that's this piece over here, we're saying it equals this, but it's got to be less than or equal to this one. And if we take the limit of this one as n approaches infinity and we get 0, it has to be less than or equal to 0. But clearly, the absolute value of r sub n of x is greater than or equal to 0. It's an absolute value, duh. So how can it be that the limit is less than or equal to 0 and at the same time is also greater than or equal to 0? Well, by the squeeze theorem, they must be equal to 0. Sorry, I'm speaking faster than I am writing, as usual. Hence, one of my favorite math words again, the cosine of x is equal to, and I'm just going to write our Taylor series for that, the sum from 0 to infinity of, and we did this in prior assignments, -1 to the k power times x to the 2k power, all divided by 2k factorial. Oh, those were the days, huh? For all x existing on the set of reals. Now, these two examples that we did showed, I think, kind of in a fun way that we can use the squeeze theorem to force an answer that works for us. But our next example is not going to converge for all x existing on the set of reals. So what do we do then? Well, in this case, remember, we basically turn these into power series. And when we're looking at power series, we can use the ratio test in order to calculate convergence, which will help us to find an interval of convergence if there is, in fact, an interval. So that's what I'm going to go back to. And if you don't remember power series, then I definitely recommend that you go back and watch our video on power series. I love power series. So even if you're like, maybe I remember it, just go back and watch it again. It doesn't hurt, and it's actually kind of fun. So here we go. This is asking us to use the Maclaurin series for f of x equals ln 1 plus x, and then find its interval of convergence. This is kind of like a well-known function. And in fact, we already found this in example number 4 from the Taylor and Maclaurin series introduction. So you can check that video as well. So this was number 4 on the first lesson on Taylor and Maclaurin series. So we found it, and it was, let's just write it down to save us some time. You don't have to redo the same problems over and over again. So it was -1 to the k plus 1 power times x to the k power, all divided by k. So we're going to use the ratio test to help us here. With the ratio test, so basically, just as a reminder, we take the limit as k goes to infinity of the absolute value of u sub k plus 1 divided by u sub k. And we're going to say that if it is less than 1, then it's absolutely convergent. And again, this is just a quick review. You go back and watch the video on the ratio test and power series if you have more questions. Okay, so wow, we're going to take the limit as k goes to infinity of the absolute value of the next term divided by the preceding term. So here we go. I'm going to substitute in a k plus 1 for every k that is in our series. What? Yep, here we go. The limit as k goes to infinity of the absolute value of, I'm going to plug in that k plus 1 term so that I have that in the whole thing. Negative 1 to the k plus 1, but there was already a plus 1 here, so don't forget that plus 1 is going to go there as well, times x to the k plus 1 term, all divided by k plus 1. But you're not done yet, because now we're going to divide, and we're going to divide by the original function. So our original function, or series, I should say, is negative 1 to the k plus 1 power times x to the k, all divided by k. Wow. Don't worry, it doesn't stay crazy looking for long. We're going to simplify now. So still we're taking the limit as k approaches infinity. And still it's an absolute value. And I'm going to split things apart and simplify and divide all at the same time. So I've got negative 1 to the k power times negative 1 to the second power, right? Because 1 plus 1 is 2, and the rule for exponents says if you're adding your exponents, they must have originally had the same base and been multiplied. Then we've got x to the k power times x to the first power. And I'm doing this division at the same time, so I'm going to multiply by the reciprocal. That means the k is going to be on top. Here we go. Down below, these middle pieces are going to multiply together. So I've got k plus 1. I've got negative 1 to the k power and negative 1 to the first power. And then x to the k power. Fantastic. Well, time to reduce a bit. Negative 1 to the k power cancels out negative 1 to the k power. Negative 1 squared is positive 1, so that's just going to go away anyways. X to the k reduces with x to the k. And negative 1 to the first power is negative 1, but then we've got an absolute value here. So I'm going to apply the absolute value there, and that's just going to become a positive 1. So this is going to look a lot nicer now. I've got the limit as k approaches infinity of the absolute value of x to the first power, or just x, times k, all divided by k plus 1. Not so shabby. And we're going to take the limit as x approaches infinity. So, I'm sorry, as k approaches infinity. So x really isn't going to have anything to do with that. So I'm going to actually pull it out to the front. So it's still going to be the absolute value of x, don't get me wrong, times the limit as k approaches infinity, because nothing's going to change with x as long as k is the thing approaching infinity. And I have k divided by k plus 1. All right, so I'm going to simplify this a bit. I'm going to need to use dividing by k party. So if I have a dividing by k party, I'll have the limit as k approaches infinity of k divided by k divided by k divided by k plus 1 divided by k. Now I say we have a dividing by k party like kind of as a joke. Really what I'm doing is I'm multiplying by 1 over k on the top of this fraction, and I'm also multiplying by 1 over k on the bottom of this fraction. So as long as I'm multiplying the same number on the top and the bottom, I'm not really changing the value of this fraction at all, but I am making it a bit easier for me to take the limit of, because now when I substitute in, or when I'm going towards infinity, 1 divided by k will approach 0. but 1 is 1 and 1 is 1. So I end up with the absolute value of x times the absolute value of 1 divided by 1 plus 0, which is 1. And 1 times the absolute value of x is the absolute value of x. But we're not done yet, because in order for there to be, for this to converge, the absolute value of x has to be less than 1. To drop your absolute value for an inequality, you're just going to make that -1 is less than x is less than +1. So x has to be in between -1 and +1. So we need to find out if it can actually equal -1 and +1. So let's check it out. I'm going to lift this up a bit. I usually like having it all on one screen if I can get it to fit there, but then I'm squished while I'm writing. So if x is equal to -1, f of -1 is equal to ln 1 plus -1, which is 0. And we're not allowed to take the natural log of 0. It's not defined on that interval. So 0 is not on the domain of the natural log. So this is undefined. Any value that's going to give you a negative log is not going to work. So I don't even have to use any of my convergence rules to figure this one out. X simply cannot be -1 because it'll create a 0 inside of our argument for our natural log. Anything that will do that is not part of your interval of convergence. Additionally, if it caused a negative inside of your argument, you would also have to reject that value. So let us continue now and test the other endpoint if x is equal to +1. Okay, so if x is equal to +1, then we have some action that we can work with, because +1 and +1 makes 2. You can definitely work with the natural log of 2. So let's check it out. If that was our x value, then we would have the Maclaurin series, -1 to the k plus 1 power times the quantity 1 to the power of k, all divided by k. Simplified, this would give us -1 to the k plus 1 power, all divided by k. Now, this is an alternating series, and the alternating series says, hey, if you've got an alternating series like this, and this is your a sub n term, the alternating part, then your b sub n term has to be decreasing, and it has to have a limit that is equal to 0 as k approaches infinity. So your b sub n is just the part that's not attached to your alternating sign piece. So in this case, 1 to the k is just 1, right? Because 1 to any value is 1. So our b sub n term is 1 divided by k. And that is definitely decreasing as k approaches positive infinity. So we can say, now let's take the limit. The limit as k approaches infinity of that b sub n term, well, that's obviously equal to 0. As your denominator gets really, really big, your numerator is staying 1. This guy's going to shrink down and approach 0. So this converges by the alternating series test. What did I write? Converger is. Oh my, Mrs. Rajewski. Okay, so what that tells me is that 1 is included on our interval of convergence. So let's finish this bad boy up. Therefore, the interval of convergence is -1 to +1. Oh my, and we should include +1 because it is part of the interval of convergence. Bada bing, bada boom. Yay! All right, so I am going to do another video, and it's going to be on composite functions for Maclaurin series. So before you get started on your MyLab and Mastering, please make sure that you watch the next video. If you're working out of the textbook, then please use this problem set. Thank you very much, and I hope you guys are having a wonderful day.